أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله and a very good afternoon to everybody. We pick up from the last lecture 3. We learned about the transmission line theories and the types and their how they propagate and everything. This lecture 4, we will learn about how to design them. In book David Poser, you will already find these things in chapter 3. So based on chapter 3, this lecture is actually designed, where we will learn about the cohesion line cable design, strip line design, and the micro strip line design, how we're gonna do it. Okay, so having further delay, we will move on to the coaxial cable first. Here I have already shown you the construction of the coaxial cable. However, this construction of the cable, this no need to design. Okay, our outer jacket, okay, and the thickness of this negative or we call shielding for the coaxial cable. However, important thing is the distance. You can check. You can check here if you see the cross section view. So this indicates actually the center conductor. This portion, this is dielectric, and then this is the outer with this shielding. However, this shielding, you know already, this is this is negative and this is a positive. So this is a live wire and this is a ground, also we can say it. So based on the principle of design, these are the basic very important thing, that the dielectric material have a constant which we call dielectric constant. We call it sometimes dielectric permittivity. Basically that is the dielectric permittivity, which is actually also can be called that relative dielectric constant also. Okay, where we can find 3 parameters basically. So one parameter is ER, another parameter is inner diameter. Inner diameter is basically inner radius. It can be actually twice of the inner radius. So you know it, but I just mention it because later on you just don't get confused if the radius is given. Okay, and then the outer diameter, which is the twice of the outer radius. Okay, now these things actually can come with different input impedances. It can come with 50 ohm, it can come with 75 ohm, and so on and so forth. Basically, in our LAN, WAN, and Ethernet network connections, or the cell tower connections, where the mobile is connected with this one, the base, the cell tower, the rooftop cell towers, the big towers you always see, these all are actually 50 ohm coaxial cable lines. Okay, and in the WAN and LAN, local area network or wireless area network, or Ethernets, where the computer is connected, intranet also, the 50 ohm cable lines are there. Okay, however, for the network, for the TV and everything, cable TV and everything, usually the industrial grade is 75 ohm. Okay, so this is important actually, because based on this one, the cable is actually designed. So basically we have 2 types. We have well, there are many actually, there are few others, but industrially we have 2 different grades, which is 50 and 75 ohm characteristics impedance coaxial cables. Okay, now this characteristic impedance, since this is very important, there is an equation that we need to follow about this. This is very, very clear, crystal clear, that this is ER, right, as we have seen already. So we have ER here. So the characteristic impedance, to calculate or to estimate any characteristic impedance, D, if you know the D outer diameter and inner diameter, or you know the ratio between them, and if you know the dielectric constant of the dielectric material here, then you can easily find out the ohmic value of the characteristics impedance. It can go other way around also, that if you know about the the characteristic impedance of the line, and then you know the dielectric constant, and you know one of the, either you know the outer or inner diameter, then you can actually estimate what is your inner or outer diameter. Okay. One more thing we can design from here is the limit, frequency limit, means how maximum this design can tolerate frequency wise. Okay. So if you know C is the speed of the light, so here, and then pi you know already, d and big D and small d you know already, and ER and epsilon r is the relative permittivity and permeability of the dielectric respectively. So if you know the value, then this can be estimated directly. Okay, in the example we will do it, no worries. And then we need to do one more thing, is we need to estimate the loss. Okay, the conductor loss I am not putting, is very complex to, sometimes very complex to estimate, but that is not our goal of this course. Later on in the higher studies, or maybe when you go for companies, you will learn it inherently actually. Okay, so here we will learn about the loss due to dielectric only. And again, this is the equation for this, and then remember one thing, this is this is what we call dissipation factor, tangent delta. Okay, and the lambda is a free space wavelength. So I supposed to put a 0 here, but that's my mistake. But however, you will listen to my words that this lambda 0 is a free space wavelength. So if you know the frequency, then you can calculate this one, and then you can, if you know all these values, you can find what is the loss per meter in dBs. Okay, but if you don't want to, you are lazy to calculate this one, you can directly put the value of gigahertz here, then by this equation you can find the loss also. Okay, so these are the three things you need to know about the design of the coaxial cable. Now we go for an example. Okay, the example says that a 50 ohm coaxial cable, 50 meter long. Okay, so length of the cable is known now, and what is the characteristics impedance of the cable, that is given also. Okay, it's given for you to twist. Okay, for you to test. Okay, no problem. The inner diameter is 1 mm given. A dielectric material Teflon is used in the cable that has a relative permittivity and permeability of 2.2 and 4 pi into 10 to the power minus 7 respectively, I would say. Okay, so the permittivity and permeability is given. Okay, as this is permittivity and this is permeability. Now is the loss tangent or dissipation factor value is 0.009. You need to estimate the dimension, outer dimension. You need to estimate the maximum frequency, and you need to find the loss of the entire length of the cable at 3 gigahertz. Means in 3 gigahertz what will be the loss for the whole cable. So now the dissipation factor or the loss tangent, I told you already, this one. Okay, so it is given also, so it's easy as that. So we go for the solution. The solution says this, so here log, so you need to convert them like this. Okay, I think I consider that you know it. Okay, I consider that you know it, but I'm telling you that you multiply with this, and then you divide with this, and then you anti-log the whole thing, will give you only d by big D by small d, and then from multiplying small d you will get this, and when you put these values everything, you will get this